Tashdari everybody. So last class we talked about we studied fourth chapter, that is magnetic effect of current or moving charge. So the most important part we studied last class is the magnetic effect. That means if I have magnetic fields and if a charge is moving in a magnetic field, charge experiences a magnetic force, and this is the force that is experienced by a moving charge. This is the force experienced by moving charge. And if I get a current wire in a magnetic field, then current wire experience a magnetic force, that is this magnetic force. And we have learned that the direction of force for both the moving charge and a current is perpendicular to plane containing velocity and magnetic fields. For current, it is perpendicular to a plane containing length of wires and magnetic fields. This is what we studied. And then what we studied is then we studied is a Biot-Savart law, how to find out magnetic field, and this is what we studied. So in sum, we say that this is magnetic field due to a small current element is given by mu naught time 4 pi I dl divided by r cube cross r. This is the vectorial representation of, and that is what we have. And then magnitude wise, this is given by mu naught 4 pi I dl sine theta divided by r square, and direction of magnetic field is perpendicular to a plane containing dl and r. So this is what we have. So direction is into the planes, and this is what it is. And then again, for your kind information, I would like to bring a small corrections for last class regarding this, right? So last class, what I have done is I did reciprocally, right? For this last class, what we have done is this is centripetal force is provided by magnetic force. All right. So this is cancelled out. Mv divided by r equal to qb, and r has to be like this. So yesterday I just did reverse thing, right? Actually, I have put like this. R goes here. Look at here, right? This r goes here, and then n qb. All right. So therefore, r is equal to Mv divided by qb. This is the correct one, right? So yesterday I just did the opposite one. So kindly correct this. And then if it is so, then I will do a small correction also. Then only thing is what you have to do is to just reciprocally, right? Then time period is going to be 2 pi r divided by velocities, and r is going to be mv divided by qb, and this is equal to 2 pi divided by n qb. This is the time period, and then frequency is going to be qb divided by 2 pi n. All right, this is what we need to do a correction, right? And then an angular frequency is going to be qb divided by n. So this thing you should correct. So only thing is you should know this, then every correction can be done, right? So this thing you should do small correction, right? All right. So this is all about moving charge, the part of a moving charge when put in a magnetic field. All right. Now what we are going to study is today is applying a Biot-Savart law, and we will find out magnetic field at the point on axis of circular current loops. Circular current loops. Circular current loops. So this is what we are going to study, right? So magnetic field on the axis of circular current loop. This is the circular current loop. So first let me explain this diagram first. So we would like to study a magnetic field along an axis. This is the axis. So the circular plane having a radius, circular plane, circular current loop of radius r, having current I is put in a YZ planes. This is in the YZ planes. The axis is along x-axis, and I say axis is along x-axis, and we would like to find out magnetic field along x-axis, right? So what to do is to find magnetic field at a point on the axis. So I say that O is origin, right? O is center O. Center O as origins. Alright, so X is distance, right? X distance from centers. From O, that is P, right? So we would like to find out magnetic field at a point P having a distance x distant from O. Alright, and then R is the displacement vector. Between length elements and point P. Between length elements, this is R. This is what we call displacement vectors. Displacement vector, right? And this is what we call a length element. This is what we call as length elements. Small portion of a circular loops. This is length element, current I. Alright. So this is what we have here, right? And this radius R. So now what we would like to do is we will apply a Biot-Savart law and try to find out magnetic field, right? So having this, I say that magnetic field at point P. Magnetic field at a point P is given by a Biot-Savart law, that is mu naught divided by 4 pi I dl then sine theta let's say dl divided by r square This is the magnetic field. Alright, I just write here. Okay, this is the magnetic field at the point P due to a small length element dl. Alright, small length element dl. And I say that the magnitude of magnetic field would be divided by, I have to put I current 4 pi r, this is cube, I'm sorry. This is the magnitude, right? And the direction is, look at here, the direction is perpendicular to right? So the angle is going to be 90 degrees perpendicular to DL and R. Alright? Now look at here, angle between DL and R, this angle, right? Angle between DL and R is 90 degrees. Angle between DL and R is 90 degrees, so therefore sin 90 is 1, so I put like this. Alright? So the magnetic field at the point P is going to be this is the magnetic field at point P. This is the magnetic field at point P. So what I'm going to do is, first I'm going to take a small elements and then I go on adding up all the entire element, right? That gives you circular current, right? So this magnetic field has two components, alright? This magnetic field has two components. One is perpendicular components. I'm going to write like this. Another one is along x-axis. Along x-axis. This is perpendicular component. This is, so therefore I have here, this is the perpendicular component, this is the horizontal components. So this magnetic field, total magnetic field can be resolved into two components. Alright, so this is how I have written. So now what I am going to do is, as far as the perpendicular component is concerned, the total magnetic perpendicular component due to entire circular current loop is going to be 0, right? So that therefore I just write here total perpendicular components is 0. Alright, why 0? It cancels each other. Alright, why? Because two corresponding, right? Why? Because two corresponding components, right? Two corresponding perpendicular component get cancel each other, right? I will show you this, right? Alright. So this is how it is going to get is, if I take these perpendicular components, alright, magnetic field would be like this. And then this is going to be a horizontal component and this is going to be a perpendicular component. So therefore these two components get cancel each other. This is how it shows, right? So therefore we don't need to mention a perpendicular component. Why? Because when I take a entire contribution from an entire circular current loops, all the perpendicular components of a corresponding sides, these two are the corresponding sides, get cancel each other. So therefore the net magnetic field due to perpendicular component is going to be 0, right? So therefore I just write here, this is going to be 0. Just the total, right? I just write it 0. Alright. Now what about, right? Now horizontal component, right? What about horizontal components? Then what about horizontal components? So horizontal component, this becomes dB cos theta. Look at here, theta is this is theta, and this theta is that theta. Why? Because this is perpendicular, right? This has to be perpendicular to the plane containing R and L. Alright? If this R and L, this is going to be perpendicular to a plane containing R and L, even only if this theta is equal to that theta. Alright? Again I am repeating. Since the d theta has to be perpendicular to a plane containing R and dLs, and this is going to be a perpendicular if and only if this inclined, right, angle must be equal to that inclined angle, right? So therefore I put this is theta, right? So I say this is going to be dB cos theta. Okay. So therefore, dB, this is going to be, how much is dB? Mu naught 4 pi I dl R. How much is going to be R? So this R is going to be, look at here, this R is going to be, this R I'm going to here R square is going to be x square plus R square. This is Pythagoras theorem, right? So I'm going to substitute here x square plus R square and then cos theta. And what is theta, right? Cos theta. Cos theta is equal to, I'm going to say cos theta is going to be base divided by hypotenuse. Alright. So therefore hypotenuse is equal to R, that is going to be x square plus R square root. Root is going to be power of half. Okay. So therefore now I'm going to get this is going to be mu naught I dl R divided by 4 pi power half plus 1 is going to be 3 by 2, right? So this is going to be 3 by 2. This is what I have. Alright. Now this is due to a small element, right? This is due to a small length elements. Now for entire, right? So magnetic field due to entire magnetic field, right? Magnetic field due to, I say, this is I write here magnetic field I write here field, right? Field due to entire circular loop is circular current loop is going to be there will be only horizontal component, so I'm going to put x. Why? Because perpendicular component get cancelled out, and this is going to be 0, what I told before. So therefore this is going to be mu naught I. Now look at here, this is the small element, right? So I have to sum up this. If I sum up, I'm going to get entire circular loop, and entire circular loop is what I call as 2 pi R. Alright, this is what I have. Alright, this is the circumference, right? This is the circumference, the length of entire circular loop. Alright, field due to entire circular current loop is going to be this. Alright, now I just say this cancel out with pi 2, and then R into R is 2R, mu naught I 2R square 2x square plus R square 3 by 2. This is the final answer, right? This is the final answer. Now the magnetic field, the direction of magnetic field would be bx, that is b I cap. Why? Because x-axis is along unit vector I. Alright. So therefore magnetic field would be equal to alright, magnetic field would be equal to bx I cap mu naught I R square divided by 2 I cap. Alright. Now this is along my axis, right? This is along my axis, right? Okay, now what I would like to do is this is one very important expression. This is one very important expression. So if I have a circular current loop, you won't get the magnetic field in a perpendicular components. Magnetic field would be only in only along axis. Magnetic field would be only along axis. Magnetic field would be only along axis, and this much magnetic field. All right, this much magnetic field, and then since this goes like this, along my x-axis I have written I cap. Okay, and then I can use a right-hand thumb rule to give you the direction of magnetic field. So this is the direction of current, right? This is the direction of current, and thumb is the direction of magnetic field. So magnetic field goes like this. Magnetic field goes like this. If the direction of current is just the opposites, then direction of magnetic field is minus I cap. If direction of magnetic field is in this way, right? Look at here, like this. So it is along I cap. If the direction of magnetic field is just the opposite, right? Then direction of magnetic field is minus I cap. That you should keep in mind. That you should keep in mind. Now next is, what about at the center of circular current loops? At the center of circular current loop, at the center of circular current loop, x is going to become 0. X is going to become 0. If x is equal to 0, then the point exactly coincide with the center of circular loop. So therefore equation reduced to what? Then I have equations. B is going to be mu naught I r square to r3, alright, I kept. So finally I write here, this cancel out, mu naught I divided by 2r. This is magnetic field at the center of circular current loop. This is a magnetic field at the center of circular current loops. Alright, so I am going to put I kept. I am going to put here I kept. Alright, I am going to put here I kept. So this is magnetic field at the center of circular loops, right? So I just say I have like this, current goes like this. What is magnetic field? Field direction is this. Field direction is this, and magnitude of field is given by this. Alright. So I have done the entire job, that is how to find out magnetic field on the axis of circular current loops, and then we have learned that it is only the horizontal component, that is component along the axis, which contribute magnetic field at point P. There is perpendicular components for every length element, but however, for entire circular current loops, the net magnetic field component, perpendicular net magnetic field perpendicular component is going to become 0. So that you should keep in mind. Very, very important, right? Alright, this is what I have. This is how you do. So this is something like this. If I have a circular current loops, magnetic field would look like this. Look at here. And this is along axis. This is along axis. This is along axis. So I have one like this. So this is what I have, right? This is what I have, and then magnetic field is along I cap, right? And you will be having, right? Since we are talking only about magnetic field along axis, we took only this. Alright, so that is what I have, right? So now if I have n number of turns, right? So far we discussed only one turn, right? If I have n number of turns of a wire, so what I am going to do is I am going to put n. Right? I'm going to put n, right? For one turns, I just say for one circular loops, that is current loops, magnetic field is going to become mu naught I divided by 2r. So therefore, if I have a n number of turns, then magnetic field is going to become for n turns. For n turn, magnetic field become n mu naught I divided by 2r. That's the simple answer, right? Okay. Okay, now I'm going to do a very important concept for finding a magnetic field. That is ampere. These are the example, right? This is what three-dimensionally looks like this. Magnetic field, right? These are the magnetic field, right? You do look at here, right? This is the center, axis of. This is again diagrams, right? These are the diagrams. Okay, now I'm going to do what we call as Ampere's circuital laws, and this is the second method for finding out magnetic field due to current loop or current elements or current wire. All right. So look at yours, and I would like to bring electrostatics here. When we talk about electrostatic, we have two laws, right, for finding out electric field. One is the Coulomb's law for a discrete charge, all right, and another one is the Gauss's law for continuous charge distributions. Again, similarly here, right, for magnetic field also we have two laws. One is what we call as Biot-Savart law, what we have done so far, and then second one is what we call as Ampere's circuital law, and this is very similar to Gauss's law, much simpler, but you cannot apply it to so many situations, right? Why? Because it requires symmetry. I told you last time, right? In Gauss's law. Now, to tell you about the Ampere's circuital law, what you should know at least is we have to consider Amperean loop, and this is what we call as Amperean loops. This is what we call as Amperean loops, right? So this is what we call as, before I write it, this is what we call as, I have a wire current like this, I have a current like this. So to find out magnetic field along any loop, right? So I have to take Amperean loop. This is what we call as Amperean loops. This is what we call as Amperean loops. All right. What we call as Amperean loops. And then what I'm going to put is I have an open surface. This is the surface or boundary, right? This is what we call as a surface or boundary. And this is open surface. Open surface. And this loop is what we call as magnetic field loop. This is what we call as magnetic field loops. And this is the current. This is the current. This is the current. And this is the current passing through any surface. You can choose any surface. Here I choose surface like a pot. This is something like the mouth of a pot, and you see a circular loop, and then I have the whole entire body of a pot, and current is passing through this pot, passing through this is surface. This is a surface. So now in case of Ampere's circuital laws, current has to pass through, current has to be, right? So this is very, very important. Current has to pass through a surface. You can choose any surface. This is surface what I have chosen, right? And this is the magnetic field, right? This is the magnetic field. This is the magnetic field. Again, direction of magnetic field is given by a right hand thumb rule. All right, this is open surface. So this is what I have, right? So this law says that magnetic field along Amperean loops. Magnetic field along Amperean loops. The law says that magnetic field along Amperean loops. This is magnetic field along Amperean loops, along a closed loops. Look at here. This is magnetic field. Magnetic field along loops, along loops. Magnetic field along loop. Why? This is a dot product. This is the dot product. This is a dot product. This is a dot product. And we would like to find out magnetic field along the loop. We are not going to find out magnetic field on the surface. We are going to find out the magnetic field along a loops. Right? So this says that magnetic field along a loops is equal to mu naught times and a current passing through the surface. This is the current. This is the current passing through the surface. So current has sometime we put this like this. Current enclosed by a loop or current penetrating through a surface. Like I can give this as a IIP. Current penetrating through a surface. So this is what we talk about Ampere law. Alright, this is what we call as Ampere law. And this is going to be a magnetic field. Magnetic field has to be like this. Magnetic field has to be like this. So this is, and the direction of magnetic field, look at here, these are the magnetic field directions. These are the magnetic fields. So these are the B, right? B, right? The magnitude or and the direction of magnetic field B is tangent to the loop, and tangent to the loop, right? Direction of magnetic field is tangent to the loops, right? Normal to the current, right? Direction of magnetic field has to be a normal to the loop, right? Normal to the loop. I'm sorry, right? Direction of magnetic field has to be this, right? So this is what I have, right? So this is going to be a small length element. This is small length element. This could be a small length element. This could be small length element. This could be small length element. And this integrations, right? This integration, this is what we call as a line integral, right? Line integrals. And this integration will sum up entire loop. Alright. So this is what I have. So alright, this is what it talks about. Law states that the line integral of magnetic field along a loop C in a vacuum is equal to mu naught times total current passing through open surface. This is very important, right? So passing through open surface, this current has to pass through open surface. So mathematically it is written like this. Alright. So this is what I have in case of Ampere circular law. And then one very important point here is the magnetic field. Look at here. Point here is magnetic field tangent to the loop, right? Magnetic field tangential to the loop is non-zero. Alright, non-zero. Magnetic field that is tangent to the loops or tangential, right? Let's say tangent to the loops, right? The magnetic field tangent to the loop, the direction of magnetic field, I write here. Direction of magnetic fields that is along, alright, direction of magnetic field tangent to the loop is non-zero. This is going to be like this. Why? Because if it is tangent to the loop means then the angle is going to become 0. So therefore cos 0 is going to be 1, right? So now let's say magnetic field components perpendicular to the loops is always 0, right? Always 0. Magnetic field component perpendicular to the loop is always 0. Magnetic field component perpendicular to the loop is always 0. That you should keep in mind. Alright. And magnetic field component tangential to the loops, magnetic field component tangential to the loop is non-zero. That is very, very important, right? Why? If it is normal to the loop, then angle becomes 90 degree. Alright. If an angle becomes 90 degree and cos 90 is going to become 0. Right? Cos 90 is going to become 0. Right? So in this case, theta is going to become 90. Then cos 90 is equal to 0. In this case, theta is going to become 0. Therefore, cos 0 is 1. So this is the reason, right? This is the reason. And then I would like to do one small case, right? Magnetic field due to infinite long straight current wire, right? Magnetic field due to infinitely long straight current wire. Alright, so I'll be having like this. I have a long current wire. This is the current wire. So now I'm going to use Ampere law to find out magnetic field. I take this is a loop, circular loops of radius r. This is a circular loop of radius r, circular loop of radius r. And now I have to put a surface. This is the surface. I am going to take this surface. This is the surface. This is the surface. This is the surface. And you see, the current is penetrating through a surface. A surface is just a plain surface put over this circular current though. And this current I is penetrating through a surface. This current I is penetrating through a surface. So now I am going to use Ampere law. I am going to use Ampere law, and Ampere law says that this is equal to mu naught I. I is a current. Okay, so now look at here. This is going to be since it is a tangential and 0 degree, so therefore this is going to be L mu naught I. What is the L? L is 2 pi r, which is equal to mu naught I. And what is magnetic field at this point? Magnetic field at this point is going to be alright, so this is current is radius is r, so I'm going to r. This is the magnetic field. This is the magnetic field. This is the magnetic. So therefore, if it is current is in these directions, the direction is given by right and thumb rule. So this is what I have. This is what I have. So look at here, thumb, right? Goes like this. This is the direction of current. This is the direction of magnetic field loop, right? So field loop would be like this. So these are the tangent, right? These are the tangent, right? B so what is magnetic field at point P? Let's say this is some point P. Magnetic field at point P is given by these equations. Alright. Alright, so with this I'm going to stop for a while. Alright. So next class I'm going to do the application of, this is a small application of Ampere law, and next class I'm going to do application of Ampere, that is solenoid and toroid. Thank you.